Okay, so welcome back. This is the third part and final part of Lecture 2. And we're going to talk about the gamma distribution. So this is the gamma distribution here, and it's got some nice properties. A couple of nice properties is that, it's kind of bounded on this left side by 0, and it's got what we call quite a long tail. It can extend quite far out to model, extreme type events a little bit better than maybe something, say, like the normal distribution. So again, we've got, let's say, some observed data here. Maybe these are flood flows. And what we want to do is we want to fit some sort of mathematical model, again, using what we call the gamma distribution, that PDF, and fit it to our data so that we can say something about these really extreme events in case we don't have any observed. So the PDF here is described by this function, right? And so we can see it's got, again, our kind of the common bit, this x value, right? So, the events that we're talking about. And then we've got these parameters. So instead of mean and standard deviation, we have these parameters A and B, right? And then down at the bottom, we have this gamma function. And the gamma function is just simply, A, or that A parameter, minus 1. And it's the factorial of that, right? So if A was 5, it would be 4 factorial. So the CDF for this, right? Again, this is in generic terms here. It's an integral, right? So we're gonna be talking about the area under this curve. And again, it's not something that we're gonna try to deal with analytically. We use tables, we use Excel, we use numerics to deal with this. We don't try to integrate this thing by hand or something, right? Okay. So again, the whole idea of this is that we're going to take that equation there, right? We're going to take this equation right here, and you could put this in Excel. I've done it myself. You could put this in Excel, and for all these different values of x, pick an A and B parameter and spit out a bunch of different values of x so that we would fit this curve to our data. And the thing that fits the best, those are the parameters for the gamma distribution that we would use then going forward, right? So now these parameters, they're called the shape parameter and the scale, or sometimes people call it the rate parameter. And the shape parameter is commonly denoted by either an alpha or a k, and the scale or the rate parameter is commonly denoted by a beta or 1 over theta, right? And these things basically shape our distribution, right? And so why do we care what shape this stupid thing is? Well, the shape determines how the distribution looks, right? So we can change how skewed the distribution is, where the bulk of the data lie, how spread out, etc. And to give you an example of this, we can see right here some different parameter gamma distributions, PDFs. So here we have one where k is equal to 1 and theta is equal to 2. So we've got a lot of the data kind of lying down here around the 0 point and extending out here, but maybe not quite as long of a tail as some of these other ones. Here we have some that don't have such a low value, right? They end up, we kind of have the bulk of the distribution out here over, kind of away from 0, and then kind of going down. And then over here, this blue one is a real great example. So here, you can imagine we might not have a lot of floods that take on these low values. We might have a lot of floods that kind of lie here. And then we have the big mega floods way out here in this long tail region, right? So these really extreme events. So just by basically shifting these two parameters, we can get distributions that take on very different shapes. So the gamma distribution, again, these shape parameters, we can translate these things back to things that we're more familiar with, like mean and standard deviation, through these following relationships. And this is done through this thing called method of moments. We're not going to get into that. You could take statistics classes, you could take graduate statistics classes that look at maximum likelihood estimation, these method of moments, all these other things. I'm just going to give you their approximations, right? So here, the mean can be approximated as the alpha parameter divided by the beta parameter when we're talking about the gamma distribution. And the variance can be approximated by the alpha parameter divided by the beta parameter squared. And the skew can be defined as 2 over the square root of alpha. And why do we have skew here? Well, it's because this distribution, remember, these distributions are not symmetrical. So in this case, we have to include some sort of skew coefficient. Okay, so before we go any further, I'm just going to put this funny little comic up there Hopefully you'll read it to yourself right now, chuckle, so that when we get to the next part, you'll hate me less. And for those of you that don't know, this is from XKCD. It's a pretty funny comic online. Okay, so the last couple parts here, the gamma distribution. First, I know that you're probably upset with me, but don't worry, right? We're not gonna, it seems like we have a lot of different parameters, and it gets confusing, but it's really not, right? And most of this stuff we can just use tables, and we can look them up, and we use our return intervals, so things we already know, right? Okay, so here's an equation. It's very similar to the one we had for the normal distribution. We see that the mean is here, the standard deviation here, and we have some return period flow that we might be interested in, right? So we might want to know what's the flow for the 100-year event, right? And so what we need to know is the mean of the distribution or of our data. We need to know the standard deviation of our data. And then for the gamma distribution, instead of a z, we need to use this thing called k. And k is made up of a couple pieces. It's got the skew inside of it, and it's got the return period. And this k is called the frequency factor, and we basically look it up in a table. So in the textbook that I'm using at Platteville, or that we're using, you would look up this on table on pages 195 to 196. Otherwise, you could go online and look this up, or do this in Excel. So let's look at an example here. And hopefully it won't turn you, or maybe you want to be turned into the statistical Hulk, I'm not sure. So let's look at an example, continuing with this silage data that our hydrology textbook uses, right? So this is example 312 on page 197. We want to know what's the 100-year flood flow, again, but we want to know it now using the gamma distribution to estimate it, instead of using the normal distribution like we did in the previous lecture segment, right? So the first thing we need to do is, just like with the normal distribution, we need to calculate the return period, we need to calculate the mean and the standard deviation of the stream flow. And in the textbook, they've given us this, but we could do this for any data set if we go get the data, right? So we know from the previous example, we're talking about 100-year flood events, so we know what that return period is, we can calculate that. And we've been given the mean and the standard deviation. So the next step is we've got to find the skew coefficient, right? And it might be useful to rearrange alpha and beta and put them in terms of the mean and standard deviation of the data. So for instance, doing a little math from the equations that we talked about from the method of moments equations I gave you a couple slides previous, alpha, if we do some rearranging, we know that alpha is actually equal to the mean squared over the standard deviation squared, right? So we could do that, and we could figure out what alpha and beta are in terms of mean and standard deviation. So, okay, we want to find the skew coefficient. We know that from our book, it says skew, and from the previous slide, skew is 2 times the standard deviation divided by the mean. So if we know the standard deviation and we know the mean, we can plug those numbers in. And it turns out in our example here, using the textbook, that the skew coefficient is 0.789. Okay, so they plugged in the standard deviation, they plugged in the mean, that was the value that they got out. Now, we're talking about the 100-year flood events here, right? So we're going to be working down this column in our table, and again, these tables are on pages 195, 196. We're going to be working down the 100-year return period column, and we've calculated now a skew, and we can see all these different skew coefficients in our table to the left, right? So we've calculated a skew, and we said that skew was 0.789 or 0.79. So somewhere between 0.7 and 0.8 here, closer to 0.8. So if we read across the table, we find that our K value is something like 2.891 or 2.889 or something, right? So something closer to 0.8. So, if we're going to be really rough about it, we would just pick 2.891. So now all we need to do, right, is take that K value that we calculated, stick it in here, multiply it by the standard deviation of our data, multiply it by our mean, and we get what our estimate of the 100-year flood flow is using the gamma distribution. So make sure you complete that part and fill out that example nice and fully in your own terms. In the notes packet packet that you've got, the notes handout, and then we'll do some examples when we meet again for next lecture. But that's the end of lecture 2 here.